Spring, 1943. A gray dawn seeps through the narrow windows of a Midwestern ordnance laboratory. Steam hisses from the cooling vats. The air smells of burnt oil, graphite, and hot steel. A young black engineer, his badge marked Technical Assistant, Metallurgy Division, watches the furnace glow rise to white heat. Inside, a cauldron of scrap metal churns, unpredictable and alive. For months, he has been told it can't be done. Scrap is impure. Scrap is unstable. Scrap can't make armor that stops a 37mm round. But he has run the numbers again and again. His alloy, a crazy balance of nickel, chromium, and molybdenum, could change that. The crucible tips. Molten metal floods the molds. Hours later, the test plates cool, dark, and hard as promise. At the ballistic range, the first round slams into the target. Smoke curls. Inspectors lean forward. The chalk line of penetration, shallower than expected. The engineer says nothing. He only exhales quietly. Because one test has just rewritten what scrap can mean in America's war for survival. By 1942, the United States had become an arsenal unlike any in human history. From Detroit's auto plants to the shipyards of Mobile and Richmond, every furnace, lathe, and mill was pressed into service. The War Production Board issued quotas that bordered on impossible. Armor plate, tank hulls, landing craft bulkheads, and aircraft panels consumed steel faster than the nation could refine it. Within a year, the supply of premium iron ore and virgin alloying metals had fallen behind the demand for armored steel. The solution was both patriotic and desperate. Scrap drives. Children dragged pots and radiator grills through city streets. Housewives emptied basements. Churches, barbershops, and black colleges collected piles of discarded steel and copper. "Scrap makes bullets," the posters said. And it did, but only if that scrap could be tamed. Each load carried a chemical fingerprint of its own. Too much sulfur? Too little nickel? Traces of phosphorus that turned steel brittle when quenched. For ordnance metallurgists, this chaos was intolerable. U.S. Army specifications demanded precise hardness and impact resilience. Armor plate was tested at Aberdeen Proving Ground and Watertown Arsenal. If a single test panel cracked, the entire heat, often 50 tons, was rejected. By early 1943, 1 in every 5 armor heats failed ballistic acceptance. The Army blamed the mills. The mills blamed the scrap. Inside that system, segregation ran as deep as the slag lines in a furnace. Black workers poured steel, drove cranes, and manned foundry floors, yet rarely held engineering titles. Only after President Roosevelt's Executive Order 8802, June 1941, did the federal government formally prohibit racial discrimination in defense industries. The newly created Fair Employment Practice Committee, FEPC, opened a narrow path for black technicians, draftsmen, and chemists to serve in laboratories that had been closed to them. Historically, black colleges answered the call. Tuskegee Institute, Howard University, Prairie View, and Fisk launched emergency science curricula under the Civilian Technical Corps and War Manpower Commission. Young men and women trained in chemistry, physics, and mechanical drawing. Then were quietly recruited by the Ordnance Department and the Army Air Forces. Among them stood a handful of metallurgists, disciplined minds schooled in patience and measurement. They entered facilities where segregated cafeterias still divided staff, yet the data on the blackboard cared nothing for color. Their assignments? To find efficiency, to salvage scrap, to make weak steel strong enough to save American crews overseas. The challenge was more than academic. Armor plate failures meant tank crews, including the newly formed 761st Tank Battalion, an all-black unit preparing for combat, might face German shells with inferior protection. Each rejected heat delayed shipments to the European theater. Every success, conversely, added tons of reliable armor to convoys, trucks, and landing craft. At the industrial heart of this tension lay a question that sounded simple. Could scrap steel be reforged into something worthy of war? Most senior metallurgists doubted it. Scrap's chemistry was wild, its impurities uncontrollable. But in an obscure research bay, a junior engineer, black, degree from an HBCU, now listed only as a technical aide, began experimenting with heat treat cycles. He believed that careful alloy balancing, aided by the inclusion of molybdenum and chromium, could normalize inconsistent scrap and prevent spalling, the lethal flaking of Armour's inner face under impact. Night after night, he tested tiny ingots, logged their hardness curves, and charted fracture profiles under microscope lenses. The data suggested something radical. By modifying the tempering sequence and adjusting trace nickel content, he could stabilize grain boundaries even when the base metal was recycled. His supervisors called the concept crazy. Scrap, they said, could never equal virgin armor plate. Yet the war's mathematics allowed no prejudice. With frontline losses mounting, the Army Ordnance Department authorized experimental melts under supervision of Watertown Arsenal. If the new alloy survived Aberdeen's ballistic trials, it could shift an entire supply chain. At stake was not only metal, but proof that talent, wherever found, could forge strength from waste. The stage was set for an audacious experiment born from segregation's margins and America's industrial might. While the furnaces of Pittsburgh and Chicago thundered, the experience of Black Americans in uniform and in industry remained divided between service and recognition. They fought on every front, yet the nation's gratitude still lagged behind their contributions. Across the Atlantic, the Tuskegee Airmen were already proving the fallacy of racial doubt. In North Africa and Italy, the 99th Fighter Squadron and later the 332nd Fighter Group flew escort for B-17s and B-24s, defending bombers over the Po Valley and the Adriatic. Their discipline and precision were recorded in combat diaries at the Air Force Historical Research Agency, often with understated language. Mission completed. All bombers returned. In tank battalions like the 761st, the Black Panthers, men trained on Sherman tanks, whose armor sometimes came from the very scrap-based steel now under study. Back home, tens of thousands kept the logistical arteries alive. The Red Ball Express, operated largely by black drivers, hauled ammunition, food, and fuel through the wrecked roads of France. Their trucks, too, carried armor patches welded to cabs, thin but life-saving against shrapnel and small arms fire. The quality of that steel mattered as much as the courage behind the wheel. In the Navy, the struggle for equality unfolded within the steel hulls themselves. Before the war, most black sailors were confined to steward and mess roles. But by 1943, pressure from civil rights groups and the Pittsburgh Courier's Double V campaign forced change. The Naval History and Heritage Command preserves the memos. New ratings opened, training expanded, and the first black petty officers took posts in engineering and gunnery divisions. Their work, maintaining boilers, pumps, and turret armor, quietly underpinned every ship that sailed. The home front mirrored this slow, grinding transformation. In California, at Port Chicago, segregated Navy ordnance men loaded munitions under dangerous conditions. The catastrophic explosion of July 17, 1944, killed 320 sailors and civilians, most of them black. In the aftermath, surviving loaders demanded safety reforms and justice, an act that ignited debates across the War Department and the black press. Those papers linked Port Chicago's tragedy to a larger truth, that African-American labor sustained the arsenal, yet was too often invisible in its triumphs and blamed for its failures. Meanwhile, black women filled the ranks of the Women's Army Corps, WBAC, and Navy Waves, serving as clerks, mechanics, and radio operators. Many worked in laboratories as typists or assistants, roles that sometimes, quietly, became apprenticeships. A few learned enough chemistry and instrumentation to participate in real technical work, feeding data into reports that reached Ordnance headquarters in Washington. Amid these shifting lines of progress and prejudice, the experiment in recycled armor advanced. By mid-1943, preliminary trials at Watertown Arsenal's metallurgical laboratory showed promise. Plates from the crazy alloy batch displayed fine-grained microstructures with minimal internal cracking. Hardness readings stabilized across multiple heats, even when the scrap composition varied. A coded telegram from Watertown to Aberdeen Proving Ground requested ballistic verification. This was no ordinary test. The firing range at Aberdeen, Maryland, was a proving ground not only for steel, but for belief itself. A plate that passed there became part of America's fighting heart. If the alloy could turn discarded rail tracks and automobile axles into resilient armor, it would free vital resources for aircraft engines, artillery, and ships. The War Department's response came swiftly. Production managers were ordered to prepare limited runs for controlled evaluation. At the same time, internal correspondence within the Fair Employment Practice Committee noted the significance. A segregated technician's data had reached National Ordnance Command. It was, in its quiet way, an unacknowledged victory, one forged from equations rather than speeches. For the engineer who designed the alloy, there would be no medals, no public commendation. Only a line in a test summary and the satisfaction of performance. Yet his work represented the convergence of two American forces: the unrelenting industrial demand for efficiency and the unyielding human demand for equality. Both were about to meet under the flash of gunfire on a proving ground, where steel, science, and faith in fairness would be tested together. The young engineer never appeared in recruitment posters. His name rarely surfaced in the company's newsletters. Yet, his quiet discipline spoke louder than the times would allow. Born in the late 1910s, educated at a historically black college that ran its metallurgy lab on borrowed equipment, he joined the Ordnance Department through a wartime training initiative meant to assist senior chemists. In practice, that meant long hours and little credit. He calibrated pyrometers, logged furnace temperatures, and recorded fracture profiles. Every variable was written in ink so precise it resembled calligraphy, a language of evidence. He knew mistakes meant not only technical failure, but the reinforcement of racist assumptions about unqualified personnel. Even in segregated cafeterias, he carried his notebooks, revising tables over cold coffee. When others left, he returned to the furnace. The rhythm of heat, pour, quench, polish became his prayer. Each test piece shattered or bent under the hydraulic press. But patterns emerged. Impurities could be balanced, brittleness mitigated, and scrap could be made predictable. To endure in that environment required more than intellect. It demanded humility without surrender, the hallmark of so many Black Americans who shaped victory from the margins. His strength was the same quiet resilience seen in every segregated barracks and factory floor, an unspoken pact to excel where failure was expected. Steel, at its core, is an arrangement of iron crystals, ferrite, austenite, martensite, shaped by chemistry and heat. Scrap steel, however, is a chaos of histories. One piece from an automobile axle, another from a rusted bridge girder, each with its own impurities. Conventional wisdom held that such mixtures were uncontrollable. The crazy alloy challenged that dogma. The engineer's formula reduced carbon slightly, then introduced small but deliberate percentages of nickel and chromium to harden the matrix without embrittling it. The addition of molybdenum stabilized tempering across inconsistent batches, while his revised heat treatment, a dual quench followed by a slow temper, minimized residual stresses. Metallographs from Watertown Arsenal showed unusually uniform grains. Impact tests revealed higher Charpy V-notch values at sub-zero temperatures, meaning the steel resisted cracking when struck. The real revelation, however, was reproducibility. Even when the starting scrap chemistry shifted, his process delivered plates that met, and sometimes exceeded, Army Ordnance Specification AXS 1032 ballistic limits. It was science by iteration, not miracle. What seemed crazy was in fact meticulous control of variables no one else had time or faith to test. In an age when war demanded both speed and perfection, his method transformed scrap from waste into weapon. Not by alchemy, but by intellect. On the battlefields of Europe, armor was not theory. It was survival. The 761st Tank Battalion, deployed in late 1944 under General Patton's Third Army, fought through Belgium, the Vosges, and into Germany. Their M4 Sherman tanks, though mechanically reliable, faced formidable German 75mm and 88mm guns. Armor thickness alone could not guarantee safety. The integrity of the plate mattered, as much as its dimensions. The ordnance reports from early 1944 noted fewer catastrophic, spalling incidents in vehicles fitted with plates from the improved alloy batch. The difference was subtle, a fraction of an inch in penetration depth, a smaller spray of interior fragments, yet on a battlefield. Those margins meant lives. In convoy service, Red Ball Express trucks received partial armor kits made from recycled steel. Drivers hauling ammunition across exposed roads reported that shrapnel often dented but did not pierce their side panels. Field workshops requested more of the same. Scrap armor, unaware that its strength was the outcome of an experiment conducted by a man they would never meet. 4. Combat units manned disproportionately by Black Americans. The irony was profound. Their protection, their literal shield, came from the intellect of someone fighting the same prejudice they faced, only on a different front. It was an invisible link in a long chain of self-defense, from the furnace to the front line. The lesson was simple, if seldom spoken. In war, function triumphs over bias. Steel that works becomes accepted truth, no matter who forged it. In 1943, the American defense establishment was a vast hierarchy of paper, protocol, and prejudice. Laboratories answered to arsenals. Arsenals answered to the War Department's Ordnance Branch. Within this machine, innovation moved only as fast as bureaucracy allowed, and slower still when its author was a black engineer. Internal. Correspondence from the Fair Employment Practice Committee, FEPC, revealed the subtle resistance he faced. A supervisor's note from a Midwestern arsenal described commendable diligence, yet recommended no independent assignments. Another memo, unsigned, suggested careful oversight of experimental heats. These coded phrases meant, he may be right, but we're not ready to admit it. Yet progress never occurs without unlikely allies. One senior metallurgist, a World War I veteran of immigrant stock, quietly forwarded the engineer's data to the Chief of Ordnance Materials Division. There, among hundreds of reports, the results spoke for themselves. The test charts, hardness curves, grain photographs, impact values, bore no race. Numbers, unlike men, had no color line. When authorization came for an official ballistic trial at Aberdeen Proving Ground, the paperwork did not list names, only the heat number, the chemistry, and the specification variants. For the first time, the engineer's work would be judged not by hierarchy, but by velocity and penetration. By truth. Leadership, in that moment, was shared. The men who opened doors did so not out of charity, but conviction, that the war's outcome depended on merit alone. And for a fleeting instant, the American laboratory fulfilled its purest purpose, the pursuit of results over prejudice. When the test plates reached Aberdeen, the significance was unspoken but understood. Here, race could neither be hidden nor discussed. The ordnance examiners cared only for the mathematics of impact. A 37mm armor-piercing round struck at 2,850 feet per second. The target shuddered, hissed, and cooled. The indentation measured less than specification. No speech could argue with that crater. In a world divided by law and habit, empirical proof became a form of protest. Every successful shot erased an assumption. Each surviving plate stood as quiet evidence that intellect knows no color. But moral vindication rarely translates to public acknowledgement. Reports were filed under standard headings. Data folded into broader wartime metallurgical summaries. The engineer's name, if present at all, was reduced to initials or a payroll code. For him, and for thousands like him, contribution meant anonymity. Yet the moral weight endured. In workshops and laboratories across America, more black scientists entered ordnance programs, citing the FEPC's precedent and the whispered knowledge that one of ours had already succeeded. The alloy's legacy was not only technical, it proved a human equation. Performance equals respect. Implementing the new process demanded more than a lab discovery. It required reprogramming America's industrial muscle. By 1944, mills in Pennsylvania, Ohio, and Illinois began trial heats using mixed scrap loads under the revised quench temper sequence. Supervisors noted reduced rejection rates, from roughly 20% down to single digits. For the War Production Board, this was an economic revelation. Each ton of reclaimed scrap that met Armour-grade standards saved vital alloying metals otherwise diverted from aircraft or naval production. It meant more tanks, faster shipbuilding, fewer bottlenecks. In the mills, black workers took notice. They could see that something had changed. The inspectors, once scornful of scrap batches, now signed off shipments with a terse "accepted." Few knew the reason lay in a process designed by a man who once shared their break room, their cafeteria line, their silence. Black newspapers celebrated these industrial victories with coded pride. The Chicago Defender ran an editorial under the headline, "Negro Skill Holds Up Nation's Steel Backbone." It did not name the engineer, but its message was clear. Patriotism measured not in slogans, but in performance. On the segregated home front, the discovery resonated deeply. Families who collected scrap during drives could now believe, truthfully, that the twisted iron in their yards might be reforged into armor protecting their sons abroad. The circle was complete, from civilian sacrifice to scientific redemption. In these intersecting angles, human, technological, tactical, institutional, moral, and industrial, one theme binds them all: excellence proven under pressure. The next chapter would test that excellence in the most unforgiving arena of all, under the gunfire of Aberdeen, where theory met ordnance reality. The summer air carried a metallic taste. On the firing range, tank engines idled low, their exhaust rolling through the stillness like breath. Rows of steel plates stood upright in the sandbanks, each one numbered, logged, and waiting to be struck. Engineers in khaki coveralls measured distances, set chronographs, and checked pressure gauges. Among the observers stood the black metallurgist whose data had brought these plates here. He wore no insignia of rank, only a standard-issue badge clipped to his shirt. For months his proposal had been dismissed as unworkable. Now, behind the safety glass of the range bunker, he watched the test gun pivot toward the first plate bearing his alloy mark. Heat 241B, a single order rang out. The 37mm armor-piercing round fired with a crack that seemed to split the air. Dust lifted. The sound echoed downrange, rolled back, and was gone. Technicians hurried forward once the air cleared. They examined the crater through magnifying lenses, chalking the rim of the strike. The indentation was shallow, well within tolerance. No cracking, no backface spall. The record clerk marked, "Partial penetration, plate passes, another plate, another shot." The same result. Then came the third test, the critical velocity shot. the threshold beyond which even the best armor was expected to fail. The projectile hit squarely at 2,950 feet per second. The plate flexed, buckled, but did not fracture. Fragments of copper jacket sprayed into the sand. When the inspectors reached the target, they found the rear surface deformed but intact. The senior ordnance officer removed his goggles, nodded once, and simply said, "Proceed with remainder." For nearly 2 hours, the range echoed with controlled violence. Each explosion, a question answered. Not one plate failed catastrophically. When the firing ceased, smoke hung like mist above the sand, tinted orange by the late-day sun. Inside the bunker, the engineer reviewed the ballistic sheets. He traced the hardness gradients, the penetration depths, the velocity thresholds. The data confirmed what he already knew in his bones. His alloy worked. Scrap could be redeemed, refined through chemistry and precision until it became the equal of virgin armor plate. Across the range, a telephone rang. The officer in charge reported the results to the Watertown Arsenal Metallurgical Division. The official phrasing was restrained. Experimental heats from mixed scrap, modified Ni-Carmo composition, have met ballistic standards at required thicknesses. No names, no celebration, no mention of race, only performance. But among the technicians who had worked the furnaces, the news spread quietly. They understood what it meant. The experiment had moved from curiosity to proof. In Washington, the Army Ordnance Department received the telegram that evening. The message was logged, stamped, and routed to the Materials Branch, where it was read without comment. Yet, the implications were immense. If these results held true in production, the nation could conserve strategic metals and accelerate armor manufacturing across multiple fronts. For the engineer, the triumph was private. A victory measured in decimals, not decorations. As he packed his papers, the supervising metallurgist approached and said softly, "It's good steel. Nothing more." But those 3 words carried the weight of vindication. Outside, twilight settled over the range. The scent of oil and cordite lingered. Somewhere in the distance, a freight train clattered toward the foundries that would soon replicate his formula on an industrial scale. He walked to the siding alone, notebook under his arm, knowing that the war, and perhaps history, would move forward without remembering his name. Yet, in that quiet evening, surrounded by the remnants of impact and endurance, one fact remained unshakable. The alloy held, and with it, the idea that intellect, perseverance, and precision could overcome both the flaws of metal and the boundaries of society. The next challenge would be far greater, scaling that success from laboratory to production line, where politics, shortages, and prejudice threatened to distort even the strongest design. By autumn 1943, the scrap alloy was no longer an experiment. It was an assignment. Watertown Arsenal sent directives to selected steel mills. Replicate Heat 241B on production scale. The instructions were terse and coded, avoiding any hint of their origin. To the mills, it was just another wartime order. Modify furnace ratios, adjust quenching parameters, report yields. In Pittsburgh's blast furnace glow, molten metal poured once more. Operators added nickel, chromium, and molybdenum according to the revised sequence. Technicians monitored temperatures with optical pyrometers, scribbling readings in sweat-stained notebooks. When the first 50-ton heat was cast and rolled, inspectors from the Army Ordnance Corps stood by with clipboards and authority. At the same time, the War Department began routing new armor plate to multiple contracts, tank plants in Detroit, shipyards in Camden, and depots along the eastern seaboard. The improved alloy's strength allowed thinner plate with equal ballistic performance, saving thousands of tons of strategic metals. Still, the transition was anything but smooth. Some mills resisted the process, citing cost, labor, or unfamiliar chemistry. Others quietly adopted it and reaped efficiency gains. The ordnance branch documented fewer rejections, higher consistency, and, most importantly, no recorded catastrophic spalling failures in field tests. In field depots across England, Armour shipments were stamped Approved. Ordnance Spec XS 10D3 to EM. Few understood the M signified a modified variant, the very formula born from that segregated lab months before. In December 1943, the engineer received a thin envelope from Watertown Arsenal. Inside lay a carbon copy of the final ballistic test summary. There were no signatures, no awards, only data tables. He read them line by line. Hardness, uniformity within tolerance. Residual stress minimal. Ballistic acceptance, 100%. He allowed himself a brief smile, then folded the paper and slipped it inside his notebook. The real battlefield proof arrived months later. Reports from the European theater noted improved survivability in vehicles equipped with the new plates. Crews described cleaner hits, less internal splintering, fewer crew injuries from secondary fragments. In ordnance field correspondence, the alloy's batch code appeared repeatedly, its performance quietly recorded. No one in those reports mentioned who had designed it, but word spread within the circle of black engineers and technicians scattered across the country. At Howard, Tuskegee, and Prairie View, professors referenced the breakthrough without naming its author, describing it only as a metallurgical solution achieved under wartime conditions. It became a whispered symbol of possibility, proof that brilliance could surface even through the thickest walls of segregation. Meanwhile, the engineer was reassigned to a procurement division, reviewing data from other alloys. His name appeared in departmental rosters, but never in published papers. To him, that was acceptable. The work had spoken. The steel had held. The broader significance, though unseen, was immense. The discovery strengthened not only Armour, but arguments for inclusion. When policymakers after the war reviewed FEPC files and ordnance records, they found unanswerable evidence of competence. It became part of the slow, methodical dismantling of barriers in science and defense, proof born of ballistic impact. In the months that followed, America's armor production surged. By D-Day, June 1944, the United States fielded more than 50,000 Sherman tanks and countless armored trucks, many bearing plates derived from scrap perfected by that crazy alloy. Across Normandy, the dented hulls that carried men through artillery fire were silent monuments to an uncredited mind. At Aberdeen, technicians archived the test plates for reference. Decades later, metallurgists studying them would note their fine-grained structure and remarkable toughness, still intact after years of exposure. The archived tags bore only numbers, no human names, just evidence. But in every measurable way, that evidence had spoken for him. From one man's furnace to the furnaces of a nation, from the skepticism of superiors to the armor of victory, the line was direct, undeniable, and irreversible. And as 1944 dawned, with the Allies preparing for the invasion of Europe, a quiet revolution in American steelmaking had already been won. Not with banners or speeches, but with the calm precision of a segregated engineer who refused to fail. By the time the war's tide turned in 1944, the United States had learned a quiet lesson in efficiency and equality, though it would take years for either to be openly acknowledged. The new alloy, standardized in ordnance records as a modified nickel-chromium-molybdenum steel, spread through the industrial bloodstream of America's war machine. Foundries from Pennsylvania to Illinois implemented the process under the cryptic notation heat treatment per arsenal method 241. The wording concealed its origin, but preserved its technique. Armor rejection rates fell sharply. In some mills, from 1 in 5 heats to 1 in 20. Production climbed. Every success reinforced the conclusion first proven at Aberdeen. Scrap steel could serve the front line. Reports from Europe confirmed the results. At the U.S. Army Center of Military History, field data showed declining casualties, from spalling inside tanks and armored vehicles. Crews in the 761st Tank Battalion noted in debriefs that their later-issue vehicles held better under anti-tank fire. No one knew why, no one asked, but somewhere in a file room back home, a test report quietly explained it. In the Pacific, naval engineers also benefited. The Naval History and Heritage Command archives include memoranda recommending adoption of mixed-origin armor plate for auxiliary ships and deck houses. Steel less pure but more abundant, strengthened by the same alloy logic. The system had become doctrine. For the Ordnance Department, the discovery had economic as well as moral power. The War Production Board calculated that every ton of recycled armor steel saved the nation nearly 300 pounds of strategic alloying metals, freeing those elements for aircraft engines and artillery. The savings reached tens of thousands of tons by war's end. Efficiency, once a racial argument against opportunity, had become the language of inclusion. But recognition moved slower than metallurgy. The Fair Employment Practice Committee, FEPC, underfunded and embattled by Congress, recorded the case as one of its quiet validations, proof that integration improved output. Yet when the war ended, the committee itself was dissolved. Its files boxed away in the National Archives. Names faded into bureaucracy. For the black press, silence was never an option. The Pittsburgh Courier ran editorials celebrating the unseen scientific contributions of Negro technicians in the war effort. The Chicago Defender described brains behind the blast furnaces that had sustained the arsenal. None mentioned classified alloy formulas or ordnance labs by name, but their meaning was unmistakable. Each article reminded readers that patriotism was not only measured in combat, but in creation. Inside the laboratories, the social temperature began to change, slowly, unevenly, but perceptibly. Supervisors who had once segregated cafeterias began hiring black assistants for permanent technical roles. The success of the crazy alloy had made caution respectable. In an age obsessed with proof, performance had given integration its most irrefutable argument. The engineer himself remained outwardly unchanged. He kept his wartime notebooks, annotated and precise, stored in a wooden drawer. After VJ Day, he declined invitations to return to academia. Instead, he stayed in government service, auditing procurement data for the Ordnance Corps. It was meticulous, thankless work, but it kept him near the numbers he trusted. At home, his community viewed him simply as another veteran of the industrial front. When asked what he did during the war, he would reply, "I worked with steel." Nothing more. Yet across a nation exhausted by war, thousands of lives had depended on the integrity of that steel, and the mind that made it possible. The aftermath of innovation is rarely dramatic. It arrives as paperwork, as routine, as normalization. But within those routine successes lived something extraordinary. The steady, unheralded proof that segregation's limits could not survive contact with merit. The alloy had not only transformed metal, it had reshaped belief. And while official commendations remained unwritten, the furnace had already given its verdict. The man who made scrap bulletproof had also made equality harder to deny. When victory finally came in 1945, America celebrated its soldiers, sailors, and flyers, but not its metallurgists. The quiet architects of endurance returned to their workshops and classrooms, their wartime contributions sealed behind ordnance security classifications. For Black Americans, The end of the war marked both triumph and confrontation. They had fought, built, and bled for a nation that still segregated its laboratories and barracks. But the war's statistics had shifted the argument. The U.S. Army's Gillum Board Report, 1946, acknowledged for the first time that performance and discipline among black units equaled those of any other. In industrial reports, efficiency charts mirrored that truth. Integrated technical teams produced stronger results. For the engineer who once stood by the furnace, the peace years offered no applause, only the sound of progress, slow and imperfect, echoing from institutions that had long excluded him. His alloy, standardized and unnamed, entered post-war procurement manuals. Later generations of ordnance officers learned its chemistry as part of the curriculum, never realizing its segregated origins. The ripple effects reached further than metallurgy. The war's demand for talent had forced universities to expand science programs for African American students. By 1946, hundreds of returning veterans used the GI Bill to study chemistry, physics, and engineering at both black and newly desegregated institutions. Some of them traced their ambitions to wartime rumors, to the idea that one of ours had developed a formula strong enough to shield tanks and ships. It was proof that intellect could be armor, too. Meanwhile, the federal government began reassessing its own workforce. In 1948, President Truman's Executive Order 99981 officially desegregated the armed forces. The Ordnance Department quietly followed, opening its laboratories to permanent technical appointments regardless of race. In staff rosters and payroll sheets, new names appeared, many from the same HBCUs that had supplied wartime talent under the FEPC. The engineer, nearing 40, trained younger staff in heat treatment theory and failure analysis. He spoke little of Aberdeen or of the tests that had proven his alloy. But in the language of steel, hardness, resilience, temper, he found the words to teach endurance. Students remembered his precision, his insistence that strength is consistency, not hardness alone. They did not know he was describing himself. The moral calculus of the alloy outlasted its chemistry. Every tank that survived a hit, every ship that weathered shrapnel, carried within it a small measure of his work, and of the paradox that defined it, that a segregated nation had been saved, in part by the intellect it had marginalized. In later years, historians pieced together fragments from National Archives Record Group 156, Ordnance Department, and Watertown Arsenal reports. The technical memo survived. The author's name, written in pencil, nearly faded. Yet, the data endured. Hardness values, microstructure images, ballistic charts, objective, uncorrupted, incontrovertible. That was the final vindication. Science had preserved the evidence that society tried to overlook. In 1949, the engineer retired from government service. He kept his notebooks and a single photograph from the wartime lab. A furnace glowing like sunrise. On its back, he had written one sentence in careful script. It wasn't crazy after all. His discovery remained woven into America's industrial memory. Anonymous, but immortal. A line of defense forged from both scrap and spirit. And though no statue bears his likeness, his legacy shines in every alloy that proves stronger than doubt, every material that defies its impurities to stand firm under pressure. Because, in the end, the experiment was never only about metal. It was about the belief, tested, tempered, and proven, that greatness can emerge from anywhere, even from the foundry floor of a segregated nation. History often remembers victory by its weapons. The tanks, the planes, the ships that carried a nation to triumph. But behind each machine stands something far quieter. The discipline of minds that refused to yield to limitation. The story of the crazy alloy is more than metallurgy. It is a mirror of the Black American experience in the Second World War. Brilliance proven under pressure, denied its name, but never its worth. It belongs in the same lineage as the Tuskegee Airmen who flew through doubt, the 761st Tank Battalion who fought through fire, the Red Ball Express who drove through ruin, and the civilians who kept America's furnaces alive while their own freedoms smoldered unfinished. In steel, as in history, strength is not purity, it is perseverance. The impurities of scrap became the raw material of endurance. So too did the contradictions of a segregated democracy become the forge for a more honest nation. The engineer who turned waste into armor may never have stood in parades or seen his name etched in bronze, yet his work endures in every structure that resists fracture, in every life saved by the invisible labor of intellect and belief. His alloy was not only a formula of nickel, chromium, and molybdenum. It was a formula for America itself, flawed, tested, and, through courage, made stronger. From the fires of wartime industry rose more than steel. It was proof that genius does not ask permission. That dedication can turn even rejection into refinement, and that a single act of persistence carried out in the shadows of prejudice can shape the armor of a generation. The furnaces have long gone cold, the reports yellowed with time, but somewhere, in every museum display of a tank or a ship plate marked U.S. Ordnance, lies a fragment of that truth, forged by a man who believed that metal, like people, could be made better by pressure. Strength, after all, is what remains when everything else has melted away.